Today we're going to be talking about optimization, and just like with related rates, the first thing that we're going to want to do is draw a diagram if possible. So a box with no lid is constructed from a piece of cardboard that measures 16 centimeters by 30 centimeters. Congruent squares are cut from the corners of the cardboard and the resulting sides are bent upward to form a box with no lid. What size should the squares be to obtain a box with maximum volume? So I have this rectangle, 16 by 30. I have squares cut out of each of the four corners. This is kind of just like a blow up of what I've cut out here. Each side of this square is the exact same, and our goal is to find out how big this square needs to be to give our box the maximum volume. The next thing that we're going to do is identify the equation. So since we're talking about volume of the box, right now I know that we have length times width times height. Obviously, I'm going to have to substitute some of these in later, but for now, that's what we're going to be dealing with. The next thing that we're going to be doing is looking at restrictions. So we have a couple of things. I'm going to be talking about minimums first. Obviously, if I'm cutting squares out of the corners, that x value needs to be greater than 0. I need to have a width greater than 0, a length greater than 0, and a height greater than 0. We're not going to be having any negative numbers here. And when I think about what's happening here, if I have a width of 16 centimeters and I'm attempting to cut two squares out of these corners, I know that there's no way I can cut out a square that has an x value bigger than 8. Even if the x value was exactly 8, I would be not having any kind of width left. So what this means is that x must be less than 8. So I now know that I have an x that is bigger than 0 and less than 8. The last thing that we're going to be talking about is the other information that I've been given. So if you can't visually see what's going on, take a piece of paper, make or rip out a corner on each of the four corners and attempt to fold this up so that you can visually see what's going on. I know that I'm going to have the height of this box equaling x. Whatever I cut this size to be is how tall this box will be. I know that my width is going to be 16 minus 2x because my width is only going to be this section right here. So the 16, take away these two corners. And the exact same thing is going to happen for my length, but it is going to be the original 30 minus 2x. What I'm going to do now is take the information from number 4, those equations that we just wrote for the length, the width, and the height, and I'm going to plug that into the equation that I said I was dealing with in part 2. So volume equals length times width times height. So I have this new equation. Everything's going to be in terms of x. My length was 30 minus 2x. My width was 16 minus 2x, and my height was x. What I'm going to do now is FOIL and expand all of this out. Obviously, I've skipped a lot of steps here. I'm hoping that by now you can try and FOIL this out on your own, but you should get an answer of 4x cubed minus 92x squared plus 480x. Now that I have this equation for the volume, if I find the derivative, or v prime, I'm going to be able to see where the maximum is happening. So 12x squared minus 184x plus 480. Now I know that if I set this equal to 0, I'll be able to figure out when this is going to be at a maximum. I can see that I can pull a 4 out of all of these. It's not really necessary. You will get the same answer if you do your quadratic formula right from this line. I just think it's a little bit nicer. Sometimes maybe if you pull that factor out, you'll be able to factor it. In this case, it's not looking like it. So I've went ahead and I've plugged all of this information in to the quadratic formula. Again, I used this A, B, and C, but if you prefer to use them from the line above, that will be fine. If I go ahead and simplify this a little bit more, I'm going to get 46 plus or minus the square root of 676. Sorry, I had to pull out a calculator for that one. Divided by 6 and that is going to be 46 plus or minus 26 over 6, which is going to leave me with the answer of x equals 20 over 6 or 10 over 3, or x equals 72 over 6 or 12. Now, thinking about the restrictions that we said or we had in the previous page, I know that this one will not work. X had to be bigger than 0 and smaller than 8. So obviously this one's not good. And so our answer is going to be 10 over 3. And we can go ahead and we can put that into a decimal for us right now, because when we get our final answer, we will be working with decimals. So x is equal to 3.33 is our one and only answer. So we know that x was equal to 3.33. This was just the equation for volume. I just brought it over because I'm on a new page. If I go ahead and I plug this in for all of my x's, I can get my maximum volume. And that maximum volume is approximately 725.9 centimeters cubed. And at this point, I can do my final therefore statement. And so a congruent square measuring 3.33 centimeters will give us a maximum volume of 725.9 centimeters cubed. Okay, so this next example says you have 24 meters of fencing to enclose a garden. The garden will be rectangular shaped and one side will be along an existing wall. So we only need fence on 3 sides. Determine the dimensions of the garden so that the enclosed area is as large as possible using calculus. So obviously you could do this question in a different way. You were doing them in grade 10 and 11. Obviously not using calculus. So I'm going to go ahead and draw this diagram. I have my existing wall already. I know that I will have 2 equal widths and a length here. Now when I think about what equations I have here, obviously I'm trying to maximize area. So I have area equals length times width. In part 3, we're going to be talking about our restrictions. I must have a length greater than 0, and I must have a width greater than 0. And obviously there are more restrictions than this. We do have the maximum perimeter being 24, but we're going to be talking about that in part 4 right now. So I have the perimeter of this, and remember I only have 3 sides, so I have the 2W plus just this 1L. I know that my maximum perimeter is 24, so I am able to plug that in, and if I rearrange, I could solve for L or W. L is just definitely easier here. I'm going to be getting 24 minus 2W. At this point, it's also easy to see that we do have an extra kind of like added restriction here. There's no way that I could have a width that is bigger than 12, sorry, so my width must be less than 12. If I had a width that was bigger than 12, I would have nothing left for my length. I would be going over that perimeter. So from here we can get to this restriction, but again, it's not really necessary to write it here. You would figure it out in the end when you went to go plug it in and you got a negative length. Now the next thing that I'm going to be doing is plugging this information into my area formula. So my length is now 24 minus 2W. I'm going to keep my width the exact same way. Now my entire equation is in terms of W, and I will get 24W minus 2W squared. Now at this time I am going to do my derivative because just like with the last problem, we know that when we find the derivative, where it equals 0 is going to be our maximum. So the derivative is 24 minus 4W. So when I set that equal to 0, I get 4W equals 24, divide both sides by 4, and I get a width of 6. So knowing that our width was 6 meters, we found that out on the last slide, I can go ahead and I can plug that into the length formula. So the 24 minus 2 times W. So 24 minus 2 times 6, 12 meters. Now, if you think back even all the way to grade 9, you did learn that when you're enclosing something with only 3 sides, the maximum is going to be double, but because this question did say I wanted you to do it in calculus, you did need to do all of this work. So I've just wrote, I started, I guess, my therefore statement. The dimensions to maximize the area are 6 meters by 12 meters, giving a maximum area of, and I haven't written this out, and you probably don't, and you can do it in your head, but we know that the area is length times width. My length was 12, my width was 6, which gives me 72 meters squared.